Lecture speaker tonight is Ian Marschner. He's a professor at the University of Sydney at the NHMRC Clinical Trials Center. He's going to talk about something that I've been pushing for a while in the branch that he speak about. He doesn't realize it, but there's this issue that we're all aware of around p-values, and I know Ian's taken a leadership role in trying to make some sense of it all. So please join me in welcoming Ian today.
Well, thank you very much. So a bit of a change of pace now. We've just been hearing about all the latest cutting edge methodology, and now we're going to talk about the humble old little p-value. I would actually challenge you there about the extent to which I'm taking a leadership role on this. Whenever I hear somebody say something, I'll respond with my opinion. Whether or not I'm a leader in this particular area, I think is open to question. But it is a topic, as we heard, that is somewhat timely to have a discussion about. There has been a lot of what you might call chatter, or if you like, controversy the last few years. And what I'll try to do is start by just reviewing some of the history, both ancient and recent history that has sort of led up to that controversy. And I'll try to, using, for example, the ASA statement as one particular pivot point, but using a number of other things as well, just distill down some of the messages that are coming, because they're not, the criticism of p-values is not a unified thing. Different people are saying different things. And so it's important that we understand the different things that people are saying. And as you can see, somewhat controversially there, clearly I'm going to be saying that some of those things are not quite correct. By the end of the lecture, I'm going to start to get a little bit out there and sort of talk about whether frequentist inference is the right paradigm for resolving this controversy, or whether we need to be talking about things like Bayesian inference and indeed other alternatives. So hopefully that gets interesting. All right, so of course we have to review what the p-value is before we start talking about it. Well, the ASA has helpfully given us an informal definition of the p-value. It's the probability under a specified statistical model that a statistical summary of the data would be equal to or more extreme than its observed value. Usually in this case, specified statistical model will be interpreted as some sort of hypothesis, some sort of thing that we're interested in investigating. And the summary of the data will be a statistic with a distribution, and the p-value will then, of course, be some sort of tail area probability, for example, from a chi-squared distribution like that plot, or some other distribution. More formally, whenever we talk about a p-value, and particularly in the sort of familiar parametric contexts, there's going to be four things that underlie that p-value. The first is a sample, and when we talk about a sample, we need to keep two things in mind. One is the observed sample, and the other is that it's a realization of a random variable. So there's a little x and a big X. There's a statistic, in other words, what the ASA statement called a statistical summary. There is a model and a hypothesis. Now, in terms of the ASA statement, they mentioned a specified statistical model. So in that sense, they're kind of combining 3 and 4 there. Usually we think about it as a model that's specified with some unspecified characteristic that we typically call a parameter. And then the hypothesis is an assumption about the value of that parameter. And then with those ingredients, then we have the technical definition, which is just a tail area probability associated with the distribution of that particular statistic under the assumption that the theta value is the hypothesized value. And there's a trivial little example there. So if we've got normally distributed observations with a specified assumption about a zero mean, and we use a particular statistic based on the square of x bar, then we'll be dealing with a chi-squared distribution to calculate our p-value. Now, you notice that none of that talks about hypothesis testing, for example. All of that is to do with just simply defining a particular probability. So why do we place so much interest in this probability? What's the intuition behind using it? What I want to do is just review a little bit of that and then sort of talk about where some of these controversies come from. The basic intuition, of course, and in some ways this is an intimidating talk to give because all of you guys know as much about p-values as what I do, but we have to review this sort of stuff, I guess, before we talk about it. The intuition, of course, is that if the p-value is small, then the observed sample is inconsistent with the hypothesis, because either what has happened is a very unlikely event or the hypothesis must be false. And in that sense, the observed sample is providing evidence against the particular hypothesis. If the p-value is not small, then the observed value is not inconsistent and it doesn't provide much evidence. Based on that intuition, the p-value is essentially, and I've put the word continuous here because this issue of dichotomization is really at the heart of all of these controversies that we talk about. The p-value is a continuous measure of the extent of evidence against the particular hypothesis. Again, we're not talking about rejecting or accepting hypotheses at this point. We just have a measure essentially of the extent of evidence against the hypothesis. Now that intuition, I would argue, is pretty natural and it's an intuition that people have been drawn to for many years. In fact, over 300 years ago, somebody called John Arbuthnot observed that in 82 consecutive years, there were more males born than females, and constructed essentially what is a p-value of 0.5 to the 82, which is an exceedingly small number. And I think possibly did the first ever hypothesis test, which was to conclude from that, from whence it follows that it is art, not chance, that governs. So the p-value is 0.5 to the power of 82, and he's conducted a hypothesis test there and rejected the hypothesis that the probability of male and female is equal to 0.5. Laplace did some similar sorts of things based on more complex models using the binomial distribution with the same sorts of data back in the 1700s as well. Fast forwarding through to the very early 20th century, the year 1900, Carl Pearson was actually the first to really introduce a p-value in conjunction with his chi-squared goodness of fit test. So that original paper introduces something that is essentially a p-value. But it's really Fisher who popularised the concept of p-values and his ubiquitous text from 1925, Statistical Methods for Research Workers. And at the same time, Fisher is kind of credited, if you can call that, with this threshold of 0.05 for p-values. Actually, what he said was a fairly innocuous statement, I think, which wasn't really geared towards a hard thresholding of p-values. He said something along the lines of, we shall not be often led astray if we draw a conventional line at 0.05. And in fact, Fisher, when he was popularising the p-value, was really thinking about p-values, as I mentioned earlier, as a continuous numerical measure of discrepancy between the hypothesis and the observed facts, in other words, the observed data. And it's really then the next guys that enter into the picture, Neyman and Pearson, who elevated this to more of a dichotomous process. And I would argue that it's actually the dichotomization part of all of this that is really at the core of the controversy, not so much the p-value part of it. And we'll come back and talk about that more. But what Neyman and Pearson did was to sort of take it one step further, and essentially what they did in constructing what we refer to as hypothesis testing was basically to partition the sample space into a section that would lead us to reject the hypothesis and a section that would lead us to, as they call it, accept the hypothesis. I prefer to use the terminology not reject the hypothesis. And hypothesis then just equates to taking a sample, checking which part of the sample space the sample lies in, and adopting the corresponding conclusion. And as we all know, it was taken up with great gusto during the 20th century, but it was not without its detractors even from early on. A guy called Roseboom, who actually not a statistician, he's more of a philosopher of science. He called it a bone-headedly misguided procedure. So there was doubt about it fairly early on. That was sort of mid-20th century. Jeffreys, the sort of famous Bayesian guy, he referred to this process, or characterised it with the sentence, "An hypothesis which may be true may be rejected because it has not predicted observable results which have not occurred." I'm not even sure that I understand that sentence, but it's clearly not very good for hypothesis testing. And this, I think, is the pivotal point. Actually, the notion of hypothesis testing, and particularly the sort of Neyman Pearson paradigm, isn't in any integral sense dependent on the concept of p-values. But we have this kind of numerical, I don't know, equivalence or coincidence, which is that you can conduct a hypothesis test numerically by calculating a p-value and comparing it to the significance level alpha. That has essentially led to a coupling of the concept of hypothesis testing and p-values. And whenever we talk about hypothesis testing, particularly if it's in a negative light, we drag p-values into the frame and criticise them at the same point. And I think a lot of the controversy around p-values is by association with the concept of hypothesis testing. And I'll sort of come back to that more as well. So if you get nothing else from these first few slides, is to keep separate within your mind the concept of a p-value and the concept of hypothesis testing. Then if we fast forward again to more recent history, and we start to see this sort of groundswell of potential controversy surrounding p-values and hypothesis testing. And in particular, there's been a groundswell, and there's a floating Zoom comment box there that's hiding my word, but the word there is dichotomania. So there's been this kind of groundswell against what we might call dichotomania, which is this dichotomization of the inference process that's inherent in hypothesis testing. And perhaps one of the most significant recent contributions to that was a paper in Nature, which was headed "Retire Statistical Significance." And one of the really important features about that paper is that it wasn't just written by some eminent commentators on statistical methodology. It was actually supported by over 800 signatories that supported the message to retire statistical significance. And you see there the old crusty statistician who I'm perhaps starting to look more and more alike as the years go on. But he's being led into the room with all the other outdated ideas, and his statistical significance is to be deposited there. Note that there's no mention of the word p-value on his book there. It's statistical significance that's being retired. And that was sort of the culmination of, you know, over the last, throughout the 21st century, I guess, a sort of build-up of this questioning of the statistical inference process. One of the early contributions to that was John Ioannidis' paper in PLOS One, I think it was, back in 2005, on why most published research findings was false, which certainly pointed the finger at the misuse of statistical significance and p-values. The psychology discipline has been quite prominent in this area. So, for example, the American Psychological Association issued some reporting guidelines that sort of de-emphasise the notion of formal statistical significance. And in fact, that culminated in a somewhat infamous editorial ban in one of the psychology journals, which basically banned the publication of p-values and other notions that are connected to hypothesis tests. That was followed, I guess, somewhat in response to that discussion, and I'm just cherry picking things here. Obviously, there was other events that occurred during that time as well. But the ASA obviously issued a statement in 2016, the American Statistical Association. I'm going to come back to that in some detail. And then there's been other contributions. For example, there's a recent whole issue of the American Statistician devoted to this topic, over 40 papers on statistical inference in the 21st century, a world beyond p less than 0.05. And then obviously the Nature article that we just spoke about. And I believe there's even a JRSSB issue that will be forthcoming on alternatives to p-values as well, although I'm not up to speed on where that's actually at. But obviously there's a lot of activity in this particular area. All right, so enough about history. Let's just dissect some of the things that are being said. And in particular, what I'd like to do is just dissect some of the different messages that are coming out of all of this commentary, because it's not a unified particular issue that's being addressed in this controversy. Different people are saying different things. And I've kind of distilled it down into sort of three broader areas that loosely we can think of as potentially good uses of p-value, certainly bad misuses of p-values, and what I might call invalid criticisms of p-values. So that's where the good, the bad, and the wrong come in. In terms of potentially good uses of p-values, not everybody is saying, in fact, it's fair to say most people aren't saying that we should be throwing p-values out. So, for example, this Nature paper that I mentioned is often mentioned as a nail in the coffin for p-values. But if you actually have a look at that paper and look at some of the quotes, here's one that I've picked out. We are not calling for a ban on p-values. So that's actually not 854 scientists criticising p-values. That's 854 scientists who are not calling for a ban on p-values. Rather, we are calling for a stop to the use of p-values in the conventional dichotomous way. So it's the dichotomania that they're worried about there, the dichotomization of the hypothesis testing process. So that's one side of it. Avoid dichotomization, but don't avoid p-values, because p-values might have some good uses. The other side of it, or another side of it, is essentially warnings against misusing p-values, because that is very prevalent. And you could argue that that's not the fault of p-values if people misuse them, but nonetheless, it is an important issue. And for example, the ASA statement is very much devoted to that side of things. So avoiding misconceptions and misuses of p-values. And the ASA statement does say, the p-value can be a useful statistical measure. So there we have another sort of moderate endorsement, but it is commonly misused and misinterpreted. So that's a sort of a flag towards potentially bad misuses. And then thirdly, the message that some people are propagating, I would argue it's much more fringe, this particular message, which is that we should avoid p-values altogether. And so, for example, Jeff Cumming down in Melbourne, who's a psychology statistician, is quite prominent in this area. And we also heard just about the ban on p-values in some of the psychology literature. It's really geared around what are claimed poor properties of p-values. For example, most researchers don't appreciate that p is highly unreliable. We should not trust any p-value is one claim. And then obviously in the Basic and Applied Social Psychology journal, they actually went one step further and said that no p-values or no vestiges of null hypothesis significance testing will be published at all. So let's just dissect those three areas before we get on to a discussion about how we might address some of these controversies. So first of all, the good. potential uses of p-values. Why would we not want to throw them out? Just to emphasise this issue, that avoiding dichotomisation doesn't mean that we have to throw them out, that we have to avoid p-values. So what useful information do p-values provide over and above other analytical tools? Let's think about what the p-value is. It's a measure of distance from the hypothesis to the sample. In other words, how far away from the hypothesis is the sample? It's a numerical, continuous measure of that. And so in some sense, and this was really Fisher's original intention, it is a statistic that can quantify the strength of evidence against the hypothesis. So if we think about that in conjunction with other useful statistical measures, many of which are kind of propagated as alternatives of p-values, we can sort of look at what useful information the p-value might give us over and above these particular measures. So here I've just plotted out, for example, 4 different sample results, 4 different studies. We've got a null hypothesis, or a hypothesized value that might be something like a no treatment effect, and then the 4 different study results. And the point estimate obviously summarises our best estimate of what that treatment effect, let's say, is. The confidence interval obviously gives us a sense of the precision and the range of plausible values for that particular treatment effect. So what additional information could a p-value give us over and above that useful information that relates to the point estimate and the confidence interval? Well, suppose we ask the question, which one of those study results, which one of those samples is further away than the hypothesized value? Which one is more extreme relative to the hypothesized value of 0, the null value of 0? I mean, the second one down, the point estimate is further away than any other. Its confidence interval is actually further away than, for example, the third one down. So its point estimate is further away. Its confidence interval, lower limit, is further away. Which one is further away from the null hypothesis? Good. I didn't hear the fourth one. I'm glad I didn't hear the fourth one, but I heard all the others. Well, I guess the p-value gives us a little bit of information, tells us that the third one's actually the furthest away. It's not like groundbreakingly central information, but it's a little bit more information than what we have with just the confidence interval and the point estimate. Now, of course, all the p-value is doing there is measuring how far away the point estimate is from 0 relative to the width of the confidence interval. Okay, so any other thing that measures that, any other one-to-one transformation of the p-value is going to tell us the same thing. I'll just give you the z value, I guess. It'll give us the same value, assuming we're talking about a normally distributed thing here. So it's not like the p-value is unique, but it gives us some additional information, and perhaps when we've got a lot of asymmetry and non-normality, perhaps it's got an additional advantage there. But the point is, it's not a totally useless measure of the extent of evidence against the null hypothesis. Yes, you probably prefer a confidence interval if you could only have one, but it does give us some information. The problem, of course, is that people go much further than that, and they try to misuse the p-value, not in any sort of devious sense. I would argue the reason why p-values are so misused is that people want certain things from an analysis, and we're going to come back to the sort of intuitive summaries that people want, and they go searching for that and sometimes use the p-value in ways that they perhaps shouldn't be. You should give me some updates too about the time. I haven't got a clock here. Yeah, sure. So let's have a look at some of these misuses of p-values, and that'll lead us into a discussion of the ASA statement, which is very much about that. So there's been a number of recent consensus statements and editorials on this issue, and that have particularly focused on common misuses and interpretations. But I should preface our discussion of misuses by saying that invariably these consensus statements have started by confirming, at least to some extent, the usefulness of p-values. So the idea that we should be getting rid of them altogether is a little bit more of a fringe argument than a central argument. But having confirmed the usefulness of p-values, there's then been quite a lot of discussion about misuses, and even advocating an end to dichotomization, in other words, statistical significance. And some of the contributions, as we've seen, are the ASA statement, the American Statistician. There was also another full-length edition of the Biometrical Journal that dealt with these issues as well, and then obviously the Nature statement. So let's look at this ASA statement in a bit more detail, because it really does drill down into the misuses and misperceptions around p-values. First of all, the title, it's called the ASA Statement on Statistical Significance and P-values. So it's a comment on both of those concepts. And in some sense, that title itself keeps the two things separate. One of the most significant things about it is it's the first time ever that the ASA has issued a position statement on statistical practice. That's perhaps somewhat surprising, given the length of time the ASA has been around. So it's clearly a very important issue. And it basically consists of 6 principles, 5 of which are warnings about misuses and misperceptions around p-values. So most of the consensus statement is about misuses of p-values. One of the principles is not about misuses. One of the principles can be interpreted as a positive statement, and that is that p-values can indicate how incompatible the data are with a specified statistical model. So that's basically consistent with what I've been saying, the strength of evidence against the null hypothesis. So there's that one somewhat positive statement, and then all the rest of the statements, or all the rest of the principles, are about essentially the so-called bad misuses of p-values. And we can break it down as follows. The first 2, principle 2 and principle 3, I'm going to come back to as well, are particularly important in terms of misperceptions around p-values or misuses. The first one is the desire to interpret it as a probability that the hypothesis is true. And so the quote there is that p-values do not measure the probability that the study hypothesis is true, or the probability that the data were produced by chance. So as statisticians, we of course know that, but that is actually probably the biggest misuse of p-values. And the reason is that people really want that. They want you to tell them what's the probability that the hypothesis is true. They want to make probability statements about parameters. I'm sure there's some Bayesians in here just chomping at them. I'll get to you, don't worry. And you know, wanting to do that leads them to misinterpret p-values. An over-reliance on dichotomization. So we shouldn't be over-relying on whether something is statistically significant or not. And that's another particularly rife area of sort of over-interpreting which side of alpha the p-value is. And then you get into some of the other ones, cherry picking, for example. So you need to be, proper inference requires full reporting and transparency. You can't data dredge and just report the interesting things. Practical significance, a p-value or statistical significance does not measure the size of an effect, and that's basically an argument for not reporting p-values alone. And that is then principle 6 itself. By itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. So you need to supplement it with those other measures, but as a supplement to those other statistical measures. it can be useful. Now, I said that principle 2 and 3, particularly principle 2, is probably the biggest area of problems. I hope you can see that. I can read out what it says. This is, I mean, there's been a few sort of studies like this. This is an example of a study where the investigators have surveyed, in this case, a collection of GPs, almost 250 GPs, and asked them about their perceptions of p-values. And what we find up here is basically over half, 54% of them, in terms of their primary interpretation of a p-value, go to that first misuse, the interpretation as a real-world probability of the hypothesis or the treatment effect being beneficial, let's say, or the null hypothesis being false or true. So they're interpreting that in exactly the way that the ASA statement is warning against, and that's basically the biggest collection of interpretations of p-values. The second biggest, I'm going to have to put my glasses on to see the actual percentage, almost 30%, 29%. So now we've got over 80% are in the first two principal misuses, according to the ASA statement. The 29% there is what they called threshold reasoning, which is around the over-interpretation of the dichotomization of p-values. And then there's a few other interpretations that make up the remaining. But that, I guess, is some empirical evidence that particularly that first misuse, that it's the probability around a hypothesis, the p-value, is a misuse or a misinterpretation that particularly non-statisticians have in the real world. And I'm going to come back to that because, again, I think that is at the heart of this p-value controversy, which is that people want something and they're latching onto the p-value to provide that, even though the p-value is not that thing. Just before we get into some of the sort of invalid arguments that I'm going to get to, the question has arisen more recently than the ASA statement over the last year or so about whether the ASA statement actually goes far enough. And in fact, there was a recent, in that special issue in the American Statistician, there was an editorial by Wasserstein et al. So he was the president of the ASA, I think. Is it? Executive director, sorry. Still important. And that editorial actually said, made the point that, you know, we've had this statement from the ASA, but it stopped short of actually advocating that we abandoned the notion of statistical significance. And the American Statistician editorial said, okay, now we're actually saying that that should actually be the case, that we have abandoned statistical significance. That's fine. That's a valid opinion to have if that's your opinion, but it doesn't actually necessarily mean anything for the validity of p-values, because as we've said, p-values are best used as a continuous measure of the extent of evidence against the null hypothesis, not in a sort of dichotomous fashion. All right, so we've done a little bit of good, a little bit of bad. Now, some things that I think are invalid statements about p-values. The first one, and we'll just get this over quickly. This one I find a little bit annoying, but we have to deal with it. It's what I might call the false dichotomy argument, which is that we shouldn't be using p-values because confidence intervals are better. And my response to that is, yes, I mean, if someone holds a gun to your head and says you're only allowed to have a confidence interval or a p-value, then I would take the confidence interval. But nobody ever really does that. We can have both. So it's a false dichotomy to say that we shouldn't use p-values because confidence intervals are better. We could just use both. So it's not a very deep point, but it's something that does crop up. Perhaps a little bit more deep, some of the claims around the statistical properties of p-values, and that it's p-value statistical properties are such that it's not useful statistically. So these are mainly around exaggerated claims of the variability of p-values. So the basic argument here is that we should not use p-values because they are inherently variable and untrustworthy, and this particularly is sort of championed under the banner of the so-called new statistics ecosystem, their term, not mine, which is the product of a couple of books, Understanding the New Statistics, Introduction to the New Statistics, a paper in American Statistician, amongst other things. And the basic notion here is that p-values bounce around so much that from study to study and have such inherent variability that they're essentially statistically useless. And my response to that is that, in fact, that's not true. So first of all, I would claim that's simply not true, that statement. P-values are variable in low-powered studies, but they're not variable in high-powered studies. So really my response there is we shouldn't be avoiding p-values, we should be avoiding low-powered studies. And of course, the lowest powered study you can have is when the null hypothesis is true, when you have 5% power. Does anyone remember what the p-value, the distribution of the p-value when the null hypothesis is true? It's uniform. It's very variable. If the statistic lies between 0 and 1, yes, p-value will be very variable when you've got 5% power. And it gradually, though, becomes much less variable as we get higher powered studies. Just to illustrate that point, I'll show you some of the, that little black box is really in a very annoying spot. We'll have to deal with that next time. But anyway, this is a reconstruction of a plot from one of the books that I referred to. And I'll actually blow up the bottom left-hand corner there, which is a particular example that I see coming up repeatedly around this particular argument. It's 1,500 simulations of a two-sample testing problem. And basically what has been presented here is a histogram of the p-value in a context where we have 52% power. So it doesn't really matter what the sample size is and what the other parameters are, but it's, for some reason, it was devised to have 52% power. And here's a histogram. And the claim is that this is kind of spread right over the potential range of p-values. So therefore, we really can't trust the p-value. It doesn't provide us with any useful information. It's interesting, though, the scale, first of all, that this is plotted on. So 90% of the range occurs in this bar, and then you've got an increasingly small percentage of the range in each of these bars as you go down. So it's quite kind of, I would say, misleading way to present this. And in fact, if you actually present it on, and so we were talking about the bottom left-hand corner there, but there are the other examples for different values of power. What you see in the top left-hand corner is the uniform distribution in the context of a null hypothesis situation where you've got 5% power. If you flash back to the way they presented it, by the way, that's a uniform distribution there. That's the funniest looking uniform distribution I've ever seen. But as we increase the power, you see that the p-value distribution does get more and more concentrated. And of course, it's kind of a tautology because if I've got 90% power, then 90% of my distribution mass, the probability mass, is going to be below my alpha. So in this case, it's 0.05. So it's kind of a tautology that you will have a very concentrated p-value distribution if you get high power. So bottom line, don't avoid p-values, avoid low-powered studies. Other arguments, unrealistic expectations about replication. So as we go from study to study, the p-value can bounce around, but that's the same with any summary statistic. So I guess my response there would be that we should use the p-value as a summary statistic for a given sample, summarizes for that particular sample, how far away the sample is from the null hypothesis. Expecting p-values to be more than they are. So, for example, don't use p-values because they don't provide information about a practically significant effect or whether it exists. Well, yes, that's true, but the response really is that we shouldn't be reporting p-values alone. And if we report them in conjunction with other things, then we do have that information. And one other point, which is also relevant to some of the recent controversy or commentary, this issue of don't use p-values because alpha equals 0.05 is arbitrary or should be much lower. Actually was quite a prominent paper recently arguing that we should dramatically reduce our alpha. I think it was suggesting something like 0.005 as being the cutoff. And that's fine if you want to argue that. But all of that kind of discussion is around criticisms of hypothesis testing, not p-values. All right. So we've got all this controversy about p-values, right? And I've tried to argue here that they do have some useful place in statistical methodology, but the reality is that people are striving for more than what p-values can provide. And so perhaps the question is not so much is there a problem with p-values, but is this controversy just a symptom of the fact that there's problems with frequentist inference itself? If we adopt something other than frequentist inference, could we get rid of this whole controversy? And it's particularly around these probability statements about hypotheses or even confidence intervals. People like to interpret confidence intervals like that, which is wrong, but they really want to. So is the problem frequentist inference? Well, perhaps we should all switch to Bayesian inference. What does Bayesian inference give us that might help us with resolving this particular p-value controversy? Well, the really attractive thing that Bayesian inference gives us is the ability to make probability statements about hypotheses. So it begs the question, is this the solution for the p-value misuse in frequentist inference? And so I want to just discuss that issue. And basically, to think about that, we need to think about what the fundamental differences are between Bayesian and frequentist inference, and whether the differences that Bayesian inference has will deal with this controversy. So what is the fundamental difference between Bayesian and frequentist inference? Got a few ideas here. Could be Bayes' theorem. Well, that's a straw man. Obviously, it's not Bayes' theorem. Bayes' theorem is as much relevant in frequentist inference as it is in Bayesian inference. Is it the use of prior information, which is so important in Bayesian inference? Well, I would argue there, no. Frequentists like prior information. We like, frequentists would want to do a cumulative meta-analysis, for example, combine past information with information that's been collected. Is it this ability to make probability statements about parameters and hypotheses? Well, I think we're getting warmer there, but I would argue that that is a symptom or a consequence, not the actual difference. I would argue that the fundamental difference is the nature of probability. And so in the Bayesian context, probability is a degree of belief, and in the frequentist context, it's a relative frequency. And the important consequence of that distinction is that when you adopt the degree of belief interpretation, then it basically frees you up to use Bayes' theorem in ways that the frequentist can't use. And in particular, you can use it to make and update probability statements about parameters and hypotheses. So it really comes down to which one of these versions of probability you're most inclined to buy into. And so it begs the question, which one is correct? Maybe we should have a vote, do a survey of the New South Wales branch. Well, I can tell you that I'm ready here to announce which one is correct. What do you think I'm going to say? Who thinks I'm going to say frequentist? Some Bayesians? Neither. You stole my thunder. They're both right. They're both wrong. They're both useful. So in a pragmatic sense, personally, I don't think it matters which one we use. But if you're looking for an entirely philosophically satisfying paradigm, I don't think either of them provide that. And therefore, I don't think either of them can sort of fully fix this issue that we've got with p-values and frequentist inference. In my view, and I wouldn't say that I can tell you all the details behind this, but certainly in my view, if a fully satisfactory inferential paradigm is available, then it's going to combine elements of both. And the way in which it builds in sort of Bayesian type concepts could potentially be a way to expand frequentist inference in a way that handles p-values more satisfactorily. And to really talk about this in much detail, we have to get into a bit of philosophy. I really think that when it comes to the nature of probability, the philosophers actually know more about this than we do. We sort of think that we're the guardians of the concept of probability. But in terms of understanding the nature of probability, philosophers have a lot to offer here. And particularly one sort of contribution to the philosophy of probability that I'm quite attracted to is this idea of a two-concept view, which originates with Rudolf Carnap in his book, Logical Foundations of Probability. And he really argues that when you say the probability of something, that can mean one of two things. And he even goes as far as to label them probability 1 and probability 2. And the two different types of probability are one associated with quantifying uncertainty about incomplete knowledge, and the other about quantifying uncertainty associated with randomness. And they're two different notions of uncertainty and two different notions of probability. And they have names: epistemic probability, which is the incomplete knowledge, and aleatory probability, which is about randomness. And Bayesian and frequentist paradigms or notions of probability are in a sense both right and both wrong in the way they handle that. So if you think of what the Bayesian approach says, it says you're allowed to have both sorts of probability statements. So I've given that a tick. You can have probability statements that quantify uncertainty about knowledge, and they're essentially probability statements about parameters, and that's okay. And you can also have probability statements about random uncertainty. So Bayesian gets a tick for having both sorts of statement, but it gets across because it uses the same interpretation of probability for both of those statements. And I think that's where it falls down. Frequentist inference gets a tick because I think for randomness, the notion of relative frequency makes more sense, but it gets across because it doesn't allow us to make these statements that we want to make when we misuse p-values. We don't get to make statements like the probability that theta is greater than 0. And so a synthesis of the two approaches would essentially be taking elements of frequentist interpretation for aleatory probability statements and Bayesian interpretation for epistemic probability statements. And I'm sorry to the Bayesians because I've added an ish after there. It's not quite Bayesian, but it harks back to this concept, and this is actually, so these are not my ideas that I'm putting out here. This is a growing area of inference in the last few years. It harks back to this notion of confidence distributions, which Cox introduced back in 1958, but really goes back to Fisher's idea of fiducial probability. And those of you who know anything about fiducial probability probably know it as Fisher's biggest blunder, and people have tended to ignore it. But the idea behind this is that if you think about a confidence interval of a specified confidence level, and then vary that confidence level continuously from 0 to 1, and calculate essentially a one-sided confidence interval for every possible confidence level, and then join the dots, then what you get is a probability distribution. And it's not a frequentist, it doesn't have a frequentist interpretation, but that line that joins the dots is a cumulative distribution function. And Cox labelled this the confidence distribution. More recently, sort of beginning with this paper by Efron towards the end of the 20th century, talking about Fisher, but perhaps really initiated by Hampel, who was the founder of robust statistics in the early 21st century. They sort of dredged this concept back up and proposed it as a potential expansion of frequentist inference in the direction of taking in some of the positive elements of Bayesian inference. And Efron actually said maybe Fisher's biggest blunder will become a big hit in the 21st century. Cox quite recently gave a reasonable endorsement of the concept. But it's this book in 2016, which I would really commend to you, by Schroeder and Hort, Confidence, Likelihood and Probability, Inference Based on Confidence Distributions. I really would encourage people to have a look at that book. But basically the bottom line is that it introduces the notion essentially of what we might call posterior distributions without priors. And I know there'll be some Bayesians that don't like that, but at least I'm bringing in some of those Bayesian elements around probability statements associated with hypotheses, and that's really the intention there. What that would allow then is, instead of interpreting a statement like this, which is totally wrong within frequentist inference, it would allow, remember the probability 1 and the probability 2? We've got the frequentist probability using the notation PR, and then we've got the probability 2, which is this notion of confidence or epistemic probability, which comes from the confidence distribution, and it allows a probability statement about a parameter that is still consistent with frequentist principles. Frank Hampel referred to this as the Bayesian omelette without breaking the Bayesian eggs. Now, if you don't understand the significance, there's a famous quote about Bayesian inference, which is you can't have the Bayesian omelette without breaking the Bayesian eggs, which means you've got to have an informative prior, basically, I think is what the intention of that comment is. And Frank Hampel's saying, well, here's the Bayesian omelette without the Bayesian eggs. So maybe all of these concepts will lead to some grand unifying theory of Bayesian and frequentist inference. That's some way off. In the meantime, what should we do? Well, we should feel free to report p-values, but we should never elevate p-values to the most important aspect of an analysis. We should treat p-values as a moderately useful supplement to primary analyses, primary analysis results such as point estimates and confidence intervals. Consider p-values to be a summary measure of the strength of evidence against a particular hypothesis. Minimise, or some would say even abandon, dichotomization. So that's a move towards retiring statistical inference, as the Nature paper said, but that doesn't mean retiring p-values. And study the ASA statement and related consensus statements on potential misinterpretations and avoid these misuses. And the final word I will just give to this paper in the American Statistician around embracing uncertainty, that includes one of the authors of the Nature paper and Andrew Gelman, prominent Bayesian. Treat p-values continuously rather than in a dichotomous or thresholded manner, and accept uncertainty and embrace variation in effects. We can learn much by forsaking the false promise of certainty offered by dichotomous declarations of truth or falsity based on a particular p-value being attained. In other words, use p-values, but don't get too fussed about whether they're above or below 0.05, which is something you probably all already knew. All right, thanks very much.